Marcus Niel is going to present his title himself to save time.
Right, okay. Thanks very much for the introduction, and a couple of other thank yous. Thank you to the organising committee for allowing me to speak here. I also need to thank my co-collaborators on this. The names in blue there are various research students that I've supervised, and I've also got two co-collaborators in our Department of Biomedical Engineering who together with them I have looked at the constitutive behaviour of a real heterogeneous material within the context of micropolar elasticity theory. One other thank you is that some of this work has been supported by our Research Council in the UK. Very quickly, I'll just give you an overview of what I'll talk about. I'll talk about the micropolar elastic behaviour of idealized materials with periodic heterogeneity. And what I'm really trying to do is get a handle or identify the micropolar constitutive properties through experiment. But I use the term experiment in its broadest sense, and because these are both laboratory-based experiments and numerical computations. I'll talk about a problem that we've discovered, which is all to do with surface effects, and we had to talk about that yesterday, and I'll talk about how we try and get around that. I'll talk about the behaviour of a real heterogeneous material. As I say, the one that we've looked at in detail is cortical bone. And if I get time, possibly not, I'll talk about some preliminary results on heterogeneous hollow cylinders and some things that we'd like to do in future. Okay, so I'm kind of talking to the converted in this audience. So we're looking at micropolar constitutive behaviour. And the problem from an experimental point of view is that not only do I have the conventional Lame moduli here, I've got these additional moduli that I want to identify. And what do these really look like? And of course the pioneering work in this area was done by Rod Lakes. Lots of people cite the numbers that he's got for these additional constitutive parameters, and really our work has been inspired by a lot of what he's done. We've really restricted ourselves to the planar or 2D case, and what you can do is you can take these 6 elastic moduli that you have in the general theory, and you can reinterpret them in terms of a Young's modulus and a Poisson's ratio, which correspond to their classical Cauchy counterparts, and then you've got a length scale parameter associated with the couple stresses, and then this other parameter, this dimensionless parameter, the coupling number, which must lie between 0 and 1, and that coupling number, as we understand it, quantifies the asymmetry in the shear stresses. So really, our quest, if you like, is can we measure these parameters consistently, both for idealized materials that I'll show in a minute and for real materials. Well, how do we go about doing that experimentally? Well, we do what Lakes did, and we rely on the method of size effects. We all know, of course, that micropolar materials are expected to exhibit some sort of observable size effect, and you can infer the constitutive properties if you can observe that size effect. So, for example, in the case of a slender beam, which you load in 3-point bending, we might expect the stiffness to be given by this equation here. I should point out that that equation over there on the right is, although it's an analytical solution, it's a simplification, and it ignores things like out-of-plane effects. And of course it's just the solution for a slender Bernoulli-Euler beam with this correction term in square brackets at the end there, which contains the length scale parameter. A couple of points I should point out. As I've already said, we ignore, in this slender beam case, out-of-plane deformation, and we assume that the shear deformation is negligible. Hence, the coupling number is absent from this equation. And also, in everything I talk about, the length scale parameter that we use is actually a factor of root 12 times what people use as the conventional length scale parameter. As well as looking at straight slender beams and loading them in 3-point bending, I'll talk about slender ring samples that have this geometry. And the stiffness for these samples follows a very similar expression. You've got the first part of the equation there on the right gives the stiffness of a classically elastic slender ring, and then you've got this correction term here. So our experimental procedure is to load either beam or ring samples of constant aspect ratio, that's either L over D or R over T. So we keep this factor constant, but the samples are of different size. Now, classical Cauchy elasticity theory says that if the aspect ratio is constant, they should all be the same stiffness despite the difference in size. And what we do is, for these heterogeneous samples that I'll show you in a minute, we see if there's any size effect, and then we try and infer the modulus and the characteristic length parameter from that size effect we might infer, or we might observe. So what do our samples look like, or our sets of samples? These are straight beam samples, and they are just machined up out of aluminium bar stock. The largest sample here is about 0.5 metre long. And you can see that as we go down here, the samples are getting smaller, but when we load them, we keep the aspect ratio, the span to depth ratio, the same. All these aluminium bars have voids of this size, and they're also arranged so that the void centres are on this triangular array. Circular ring samples, again, we've got on the right here a set of slender ring samples which have these perforations machined into them. On the left here we've got a set of samples that have no perforations in them. We use this set of samples just for determining the Young's modulus of the matrix material. And then we've got this set of samples up the top here which have a lower aspect ratio. And I'll come back to the significance of those samples later in the presentation. In these ring samples, we made up different sets of different samples with different void diameters in them, so that we can see the influence of void diameter on any constitutive parameters we identify. Also, we have machined up with manufactured samples in which the void centres are arranged on both triangular arrays and quadrilateral arrays. So we can have a look at what effect matrix topology has on the parameters we identify. The other beauty of these very simple materials with their periodic heterogeneity is that we can build finite element models of them. And in these finite element models, we model the full geometric detail of the heterogeneity, so each void, we create a sort of unit cell with a mesh around it, and then we do a kind of naive thing in that we assemble these unit cells into a finite element mesh of the whole sample, and we assume that the mesh material behaves as a classic Cauchy elastic material. So we assign the known constitutive properties of the matrix material to the finite element model. Okay, just a couple of slides here showing how we actually load the samples. The aluminium beams loaded in 3-point bending. The ring samples are just pulled by diametrically opposed loads. We then derive the stiffness from the gradient of the measured load displacement variation. And what we tend to, or what we always find, is that the samples behave in a linear elastic manner. So we can just derive the sample stiffness from the gradient of that measured load displacement variation. Okay, so what do we get from the results? This is for the beam samples, and you can see what's happening here, that as the sample size is varied, the stiffness is changing. So the material is behaving as some kind of higher order continuum rather than a classic continuum. Be a little bit careful in how I've plotted these results, because the measure of sample size I'm using here is the reciprocal of the sample depth, or the square of that reciprocal sample depth. The reason is that if I plot the data in this manner, it should fall in a straight line according to the analytical expressions I had on the first couple of slides. And indeed, you can see here that the data does fall in a straight line, and on that plot I've got both the experimental data for our aluminium beam samples and our finite element model predictions. So plotted in this way, the size effect is apparently linear, and I can obtain the flexural modulus from the intercept here, and I can get the characteristic length from the gradient of this variation. In the ring samples, as I said already, I've got samples with different size voids, and what you see is that so you're seeing here in these results, I've plotted the data for each of the 3 sample sets containing the different void sizes. And again, you get the size effect, and you can see that at any given sample size, as the void size increases, the stiffness reduces, as you might expect, because there's just less matrix material there to support the load. Okay, what happens when I change the topology? So here I'm plotting the results of the size effect, both computed from the finite element model and measured experimentally, for the ring samples when we've got the voids arranged on a triangular array and when I've got them arranged on a quadrilateral array. And what we see here is that the size effect actually appears to be independent of matrix topology, which was a slightly surprising result to us, given the predictions of, say, simple lattice models. Okay, in this table here, I just summarise all the data we've got, and it's just a table of numbers, but I'd just like to highlight a couple of points here that I've indicated with the coloured backgrounds. The aluminium beams and this set of acrylic rings, the material there, obviously the sample geometry is different. The material, the matrix material is different, but the geometry of the samples, the geometry of the underlying heterogeneity is just a geometric scaling. And if you look at the numbers, when I normalise the modulus with respect to the matrix modulus, these numbers are quite consistent. And also the length scale, when I normalise the length scale with respect to the void size, you can see that the number that comes out there is pretty consistent. So this gives us some faith in that the numbers we are obtaining, the numbers we are measuring, if you like, have some physical meaning. If you look at the blue data here, this shows the, if you like, the dimensionless length scale, or the length scale normalised with respect to the void diameter, and there's a suggestion here that the the length scale parameter scales with the void size, which is actually quite a nice finding, because it kind of there's a nice theoretical paper by Begoni where he suggests this, and these results kind of help to confirm that. The final point to notice is if I compare this data here, where I've got the voids arranged on a triangular array, with the case where I've got them arranged on a quadrilateral array, you can see that the length scale parameter is fairly insensitive to the matrix topology. Okay, so that's identifying the length scale parameter. What about the coupling number? I said in the analytical solution we use to identify the length scale parameter, we ignore the effective coupling number. How valid is that? This is a question we asked ourselves. Well, to answer that question, what we've done is we've incorporated planar micropolar elasticity theory effectively into our own finite element formulation. With that finite element formulation, we can predict the size effect in the slender ring samples over the possible range of coupling number. And what we find is that if the coupling number, if we set it to 0, you get no size effect, so you get classical behaviour. If we set the coupling number up to almost 1, you get approximate couple stress behaviour. But you can see our experimental data lies very close to approximate couple stress behaviour. So what we then do, using our finite element method, is we throttle back the coupling number and we start reducing it away from 1 down towards 0. And as we do that, here I've reduced the coupling number in this set of data shown by the triangles. I've reduced the coupling number down to a very small value, 0.15 there, but I still get a very significant size effect, which is very difficult to discern from the couple stress case. So the argument we make is that we're not really going to be able to identify the coupling number from doing tests on slender samples. However, if we move to the less slender set of samples, and that was the set of ring samples that I had in the top of my photograph of all our samples, what we see then is that the effect of coupling number is more significant. So here I've got the coupling number set to 0.15, and we can see that we can now discriminate between the couple stress case here given by the squares and the genuinely micropolar case with coupling number 0.15 given by the triangles. So we actually do tests on these less slender ring samples where the aspect ratio, we've reduced it down now to this value of 4. And what we see in our experimental data is the size variation, the stiffness variation we measure with size is given by the crosses there. Okay, having got that data, I can try and identify the appropriate value of the coupling number here by matching my numerical predictions from our own in-house code containing the micropolar elastic behaviour. I could try and match our predictions to this data, this measured data. And that's what I do in this graph here. So in this graph, I'm measuring, in effect, the error between our predictions and our measured data against coupling number. And each data point here is the kind of cumulative error for all 4 samples that we're testing. And you can see that as we traverse through the allowable range of coupling number, we get a minimum. And we say that that minimum, of course, gives us the best match between our predictions and our experimental data, and that must be the appropriate value of coupling number. You'll notice there's actually 2 graphs here because we've compared our predictions with our physically measured experimental data and also with our kind of numerical finite element generated data. And the error is minimised when the coupling number is around about 0.175. And if we now compare our predictions with our measurements for that value of coupling number, of course they lie right on top of one another. This table here just summarises the values of coupling number that we've identified. What's a slight surprise here is how low the numbers are. Lattice models predict that these numbers ought to be higher. There is some slight suggestion in these numbers here that the coupling number may depend on the size of the voids, but it's not a strong influence in what we see in this data. Also, if you compare the data in the second row here with the bottom row, we're comparing where we've got the voids on a triangular array with where they're on a quadrilateral array, and the coupling number does not seem to be influenced by the matrix topology. Again, another slightly surprising result for us. Okay, I want to talk about a problem now that we haven't really got to grips with. In all the samples we've looked at so far, we've kind of idealized them, and we've been very clever in the way we've manufactured them so that the surfaces are essentially smooth and continuous. But in a real material, of course, there's no guarantee that you have a surface like that. The surface could look something like this. So it could be corrugated in this manner. What effect does the surface have on the size effect we observe? And we saw some discussion of this in a presentation or in presentations yesterday. Well, if we run our finite element models, fully detailed finite element models containing all the details of the heterogeneity, if we have a smooth surface, we get a stiffening effect, but if we have a corrugated surface, we get a negative size effect. And we can actually come up with a simpler model of this if we just look at a simple laminated beam. And we're certainly not the first people to recognise that a laminated beam like this behaves as a micropolar material. I think Professor Forrest identified this 15 or more years ago. But the interesting thing is, if you layer this up in this way, and you have alternating stiff layers and compliant layers, and you have stiff layers at the surface, what you'll get is a size stiffening effect. So that's what we're seeing in this graph here. And you can compute the stiffness in this case very easily, because you can analytically calculate the flexural rigidity of a simple laminate like this. But if you have the surface layers compliant, you see an equal and opposite size effect. Providing you meet this condition, that the thickness of the surface layer, so the TS is the thickness of the surface layer, the surface layer in this case is half the thickness of the stiff layer, and in this case the thickness of the surface layer is half the thickness of the compliant layer. So providing you meet these conditions, you'll get this linear variation in stiffness, we think. If you don't meet this condition, then these variations are non-linear, is what we find. And for this simple laminate material, what's really striking is that if you've got the surfaces as the stiff material, you get the positive size effect, and here we're just plotting the magnitude of the size effect against the volume fraction of the compliant material. But if you have the compliant surface layer, the surface effect is equal in magnitude but opposite in sign, we find. This is really puzzling to us. We don't have a theoretical explanation for us, so maybe somebody out there does. So when you're testing a real material, what's the surface going to look like? To answer that question, what we did is we generated this material here, this two-dimensional material, where we've got voids, but they're distributed randomly now, and they're also of random size, and then we just put lots of lines across this, and we said, what's the surface profile going to look like on average? And on average, the surface, if you put lots of lines on it and do a sort of statistical analysis, albeit a very simple one here, what you find is that the nature of the surface, the surface roughness, if you like, turns out to be about approximately half the void diameter. Okay, onto a real material, and I'll just put some results up for this. The real material that we've been looking at is cortical bone. The cortical bone, the major heterogeneity in it is this system of vascular channels, sometimes called the Haversian canal system. And halfway or partway along a long bone, these vascular channels tend to be orientated along the axis of the bone. Okay, very briefly, what do? Well, we cut out samples from one of these long bones. We cut the samples, beam samples, with the axis of the beam aligned with the major axis of the bone, and we also cut the samples transversely. We have this experimental protocol that I've outlined here, but the main thing is that we are very, very careful in how we prepare the surface of the samples. We polish them to a state where we could look at them under the microscope. And then we test them, and then we polish them further to reduce their thickness. And we test them, so we keep testing them at thinner and thinner sizes, and as we reduce the size, we also reduce the span so that we keep the aspect ratio the same, just as we did with the idealized materials. This is our experimental setup. The main feature is that we have a water bath in this setup so that we can test under in vivo conditions. Typically the experimental data, there's some hysteresis in it. We're loading, you notice, to very low loads, but we can identify the the stiffness from the slope of the loading line there. What does the data look like? Well, again, we observe a size effect, and we plotted the data here in exactly the same way as I did for the idealized materials. So as the samples get smaller, remember the smaller samples at this end, we get this negative size effect. So the smaller samples are more compliant. And we see this in both the longitudinally cut samples and the transversely cut samples, but the magnitude of the size effect is different between them. Okay, obviously I can get the modulus from the intercept here, and here I commit a heresy because I try, given that this size effect, although negative, might be of the same order as the positive size effect we would expect, I've actually cheated and I've calculated the length scale parameter. So if I cheat and calculate this length scale parameter, it happens to turn out to be very similar to the length scale associated with that vascular channel system. And just finally, there's a couple of micrographs here of our samples. So this is looking at a transverse section, and the major axis of the bone runs along diagonally across this. We can also produce some simple finite element models of our samples, and we can fit the finite element models to our data, and here we're fitting the finite element models to both sets of data the data for the transverse and the longitudinally orientated samples simultaneously, and we get similar numbers in that case. Okay, I think I'll leave it there.
Okay, thank you very much. Questions? Yeah.
I think controversy is better than calmness. I disagree with practically everything you said.
Thank you.
I have written several papers which show clearly that for the linear polar continua in the isotropic case, it is first impossible to determine the coupling number and the length scale independent of each other. So if you have a coupling number small, you can have a length scale number big, and so on. So you cannot divide the two effects. Second, I think, and this is not a proof, but I think that linear polar model is not appropriate for most isotropic materials. You need to have a higher kinematics, like a micromorphic model that we could talk about, because the length scale which you determine, and with it the coupling number, will depend critically on the smallest investigated size of your specimen. So what you can basically get is a size-dependent material coupling number, which should be an elastic modulus, like the shear modulus, which should be independent of the size, because the size effect should be related to the length scale, which you also won't return. So I think basically in the Kosovo there are problems, and if someone asks me, then I would tell there has never been identified a Kosovo coupling number and to fit into experiments.
Yeah.
But this is my point of view, and
I would actually I would actually partly agree with you. When we try and identify the length scale parameter independently of the coupling number, but we also have done work where from the experimental data we try and identify both simultaneously, and we do it by trying to match our data to predictions where we are varying both the coupling number and the length scale parameter simultaneously. But the problem with this is you're trying to fit two parameters at once, and there's all the difficulties associated with that. So we are not arguing that our numbers are definitive. We think they're indicative, approximate.
Okay, every further discussion must be postponed. Marcus is around here for the next date, and will be